Alright folks, this is a video on electric current, the electric current chapter from NJCTL, from the algebra-based physics. This is specific for Jerry Kaiser students at Perth. I'm sharing this with you as the video will not be available on the NJCTL YouTube, nor will the presentation file. Please ask Jerry to share them with you. And if you have any questions, you can contact me at my email. My name is Patrick. I'm going to narrate this for you, and you can contact me at patrick@njctl.org. So, all right, here we go. Electric current and DC circuits for the algebra-based physics NJCTL. I'm going to give you a very quick and brief video that you can go through, that you can use to accompany your problem solving. Use the problems and the discussions in this, as well as your work with other people and your instructor, in order to navigate your way through the chapter. Really, in my opinion, electric currents and DC circuits, electricity, if you want to call it that, are often seen to be magic, but in reality, it's the same physics as if you were going on a roller coaster or moving in a gravity field. What goes up must go down, but instead of moving in the gravity field, or having roller coasters or masses moving gravity fields, you have charges moving in a different type of field, an electric field. And if you keep that in mind, you won't have any problems. And then another basic set of rules, the conservation laws, come out to play. What goes up must come down. Energy in equals energy out. And what goes in must come out. What you put in terms of charge moving has to come out. This is conservation of energy and conservation of charge. Both of these quantities can neither be created nor destroyed. Keep that in mind, and you'll be good to go. So we're going to break this into 5 different topics: circuits, conductors, resistivity and resistance, circuit diagrams, and then devices that you would use to measure electricity. And we'll talk about all these in detail. So let's go fast. Our first topic are circuits, and it's interesting. I don't call these electric circuits, I call them electric circles, because circuits are circular. So keep that in mind. If you look here, this is called a schematic. An electric circuit is just a path that charge follows, and in order for that to work, it must be unbroken. So you need to have a complete circle, and we use 3 different parts for a circle. You have a battery, which is drawn with a long line and a short line, positive and negative terminal. You have a conductor, and there's a switch here. By the way, this is open, so you don't have a continuous path. And then you have some device that converts energy, a light bulb. So if I were to close this switch, so I'll close it. So now we just imagine that switch is closed. It goes down and snaps shut. Now we have a path, so you have electricity coming from the positive terminal, goes up all the way around through the conductor, which is copper wire in most cases, through the light bulb, and then back home. So I have a full circle. Again, 3 elements. You have a voltage source, a conductor, and some device to convert energy. That's called a load. Historically, or really from a physics standpoint or a chemistry standpoint, we usually say that charges, the charges that move from one atom to another, are negative charges. So it's the flow of electrons, or the movement of electrons from one atom to another. They're said to be delocalized, they can jump. But in this course, we're not going to use negative charges. We're going to say that positive charges move. So if I go back to this, if I put a proton right there, since I have a positive plate and this proton will move in that direction. And if you look, this is the conventional current flow. It's the movement of positive charge, and we do not consider the electron flow. So current is always from positive to negative, and it goes against what we know, that negative charge are the movers. So we will again stick with positive charge as being the one that moves, or the brand of charge that moves. Current, by definition, is simply the movement of charge. So just imagine I have a charge moving, and I'll draw, I don't know, a wire. The movement of positive charge within that wire past some point in space, maybe past some line, is the definition of current. So while the actual current is the flow of electrons from the negative terminal to the positive terminal, we use the convention current to model electric circuits. Again, that's positive charge moving. Conventional current is the flow of positive charges flowing from the positive to the negative terminal. And going forward, we'll use the conventional current when we discuss electric circuits. And it's the opposite of the actual flow of charge, or the opposite of the flow of electrons. The definition of electric current is that, and I'll put this into words, current is how much charge moves past or through some point in a wire, past a location, per unit time. So current is I, charge is Q, just like our study from electrostatics, and time is T. And the units for this are, or the units for current are amps, which we'll define in a second, which are coulombs per second. So we'll abbreviate that. Q is the amount of charge, T is the amount of time, and so on. So let's apply this after we restate what the units are. So amps or amperes, often called amps, are the units for electric current. So electric current is measured in amps. Sometimes you'll see it written as AMPS. Other times you'll just see an A. Other times you'll see coulombs per second. So that's amps. All three of these will work. Let's apply. You have 12 coulombs of charge passing a location in 10 seconds. So just imagine we have that wire. So I'm drawing a wire. And we have positive charge moving in this direction. That's conventional current. So I'll draw some line. Let's just call it a line in the sand. How much charge passes that line every second is the current. So we can apply the equation or define it and then solve this. Current is how much charge goes through a wire per unit time. The amount of charge is 12 coulombs. The amount of time is 10 seconds. So we have 12 divided by 10, that's 1.2. Coulombs divided by seconds, which are amps. Let's reveal this answer. And there we go. Another example, again, they're going to give you how much charge goes by and how much time is elapsed. So we'll pull a pen up. Solving for the current. Current is I. That's change in charge per change in time. That's how it's defined on the slide, so I'll write it in this manner. So there are 20 coulombs of charge traveling past some wire or through some point in the wire in 30 seconds. And we end up with 2/3 of an amp. 0.66 amps, which are 2/3. This circuit has a current I of 3 amps. And the question is, how long does it take 45 coulombs? That's the charge. So I'll write Q to travel through the circuit. Given that I is Q divided by T, we're going to solve for how long that's T. Time will be how much charge Q travels every second divided by how much current there is I. So we'll write this. There are 45 coulombs of charge divided by 3 amps, and I'll write that as coulombs per second. So we have coulombs over 1, that's coulombs, times the reciprocal of the denominator, because we'll be dividing a fraction, seconds over coulombs, and we end up with seconds. 45 divided by 3, are 15 seconds. Great work. Let's keep going. Again, we have a circuit that has 10 amps of current, 20 coulombs. How long does it take for that to occur? How long does it take for 20 coulombs to go at 10 amps? You can think about this. One amp would be 1 coulomb of charge traveling every second. So if you have 10 amps, you have 10 coulombs of charge traveling every second. If you have 20 coulombs, it's going to take about 2 seconds, or it will take 2 seconds. Again, I is Q divided by T. T will be Q divided by I. So the amount of charge are 20 coulombs divided by the current, 10 coulombs per second, 2 seconds. And the last example involves solving for Q. If you're given 10 amps of current, so that's I, in a time of 20 seconds, current is Q divided by T. So Q will be I times T, manipulating the equation. So we end up with 10 amps, which are 10 coulombs per second, times the time, 20 seconds. Cancel, cancel. 10 times 20 are 200 coulombs of charge. Last problem. Let's finish it out. I'm just going to solve this without writing the equation. All right, let's do it. Now, let's be consistent. I is Q over T. We're going to solve for how much charge. So Q is I times T. So the current is 2.5 amps, but I'll write that as 2.5 coulombs per second. That's the definition of the amp. Times 4 seconds. Seconds cancel seconds. 2.5 times 4 are 10 coulombs. Wonderful. Nice work. Go on and solve some problems. You've got it. All right, we're back. One important element of an electric circle or an electric circuit or a source of energy, batteries or batteries or sources of energy. And every battery has two terminals. It has a positive terminal. So if we look at these cells right here, these are all positive terminals, often identified with the bump, and the flat side are negative. These cells are all 1.5 volts. This cell here also has positive and negative, but that's 9 volt. So just imagine you have hills. These batteries are all hills that are not very tall, maybe only 1.5 meters of elevation change, if you want to use that analogy. This difference in potential, or potential difference for this battery, or voltage, would be a lot larger than 1.5 volts. You might have a hill that's 9 meters tall. So when masses fall down tall hills, they'll have huge potential energy change. It means they're going to go, oh, I don't know, faster, have larger currents. More on that soon. And these offer small potential energy changes. So each battery has two terminals that are conductors. The terminals are used to connect the external circuit allowing the movement of charge. Batteries convert chemical energy into electrical energy, which, by the way, is mechanical in nature because charges are moving, just like mass is moving, or roller coaster cars moving along a track. And they move because of what's called a potential difference. So this being a high potential and this being a low potential. A chemical reaction acts like an escalator, carrying charge up to the top of the hill. So just imagine you have a roller coaster and you have, let's use a different color. You have a hill and then you have, it goes down through a loop and so on. So this is doing work going up the hill. This is like a battery. So work is done on charges to take them up, and then they go down, they lose their energy. What goes up must come down. Click on the simulation in the presentation and play yourself with batteries. Check it out. Reviewing basic circuits. Electric circuits cannot have gaps because they are circles. If you have a gap, you won't have a movement of charge. The bulb has to be between the wire and the terminal or the battery. So again, you'll have a battery and then a continuous path of conductor, which you put a bulb in the middle of, and it burns. And a voltage or a battery is needed to make the bulb light. And the bulb lights regardless of where you put it in. And this is a wonderful video which is on YouTube, which uses the FET simulation of two different types of electric circles, and you can observe all three elements of electric circuits: batteries, conductors, and loads or light bulbs, whichever you prefer to call them. And as you watch this video, observe what's going on in the circuit, maybe make some notes in your presentation. You can compare it to your classmates. Tell me what the role of the battery is. Even though we just defined it, you'll be able to see that. Maybe looking at one battery versus two. How are these circuits in this similar and how are they different? Again, click on the link and check it out yourself. This is an informative video. It takes about 10 minutes to watch. Check it out. The battery pushes the current through the circle or the circuit. It acts like a pump, pushing charge or moving charge. If we're pushing charge, you're causing what's called a current. And it's the circuit's energy source. Charges do not experience a force unless there's a difference in electric potential, unless you have a battery, otherwise they won't move. And batteries offer a potential difference between their terminals. What goes up must come down. It goes from a high potential to a low. So the positive is at a high voltage or a high potential, and the negative is at a low. How will voltage affect current? If we increase the voltage, you will increase the current. So one battery will cause a trickle of charge, two batteries will cause a moderate flow of charge, three batteries, when you put them in series, will cause a great flow of charge when you put them in line. Again, check out the video yourself, take some time and watch it. And again, I want to remind you, this is just a preliminary video we're providing for you until the video gets uploaded to the NJCTL website. So a conductor is not the person who's on the train. A conductor is simply a material that charge can follow in. Conductors are usually made of metal because metals allow charges to jump from one atom to another freely with little opposition. Some materials are better conductors than others, and again, we want to have materials that allow for the free flow of electrons. And again, I'll just remind you, it's no secret, even though it's the flow of electrons, we say that positive charges are the ones that are moving. The flow of electrons, or charges, we should say, are just another word for current because it's not always electrons. Another way to look at this is that some conductors resist current greater than or a lesser extent. Can you think of a material that is a conductor, that's a metal? It's very common. They use this in your house for the wires. Think about that for another second. I'll give you the answer. In most cases, it's copper. What is the material that is not a conductor? What's the opposite of a metal? A non-metal, and an example of a non-metal that's something that does not allow charge to flow through it is a ceramic. In most cases, at least at room temperature. In the old days, they would use glass to rest wires on to prevent them from touching electric poles, and they did this because they were non-metal, and they were actually referred to as insulators. So different materials have different conductivity or different levels of conduction of charges or movement allow for different levels of movement of charge. And the opposite of conductivity is resistivity or resistance. Resistance is the opposition to the flow of charge, and we represent resistance with a capital letter R and the symbol omega. If we increase the resistance, if we increase the opposition to the flow of charge, can you predict what happens to the current? the current will go down. Check out the simulation and play with conductors. Take some time and visit. The quantitative relationship that relates current, voltage, and resistance is called Ohm's law. And Ohm's law, I'll put it into words. Current is voltage over resistance. I'm going to abbreviate, and you can write it as I equals V over R, or R equals V over I, or V equals IR. And these are the units. This symbol omega is for ohms. V is for voltage or volts. And A is for amperes or amps. Check out the music video. So in this series of problems, we're going to use Ohm's law to solve problems out. And the first one, they're asking us to solve for the current in the flashlight. So if we apply a voltage to some wire and charge travels in a circular path and it goes through a light bulb that has 25 ohms of resistance, the question is, what will the current be? And by the way, light bulbs work because of resistances. Light bulbs have filaments that offer opposition to the flow of charge. They'll start to heat up, eventually give off light and heat, primarily heat for an incandescent bulb. Enough of that, we'll talk more soon. Solving this, we're going to use I equals V over R. So current is voltage over resistance, and we're given 120 volts over 25 ohms of resistance. So volts over ohms will be amps. And let's just save ourselves some calculation. We'll just reveal the answer. We get 4.8 amps. If we were to increase the voltage, let's just play for a second. What would happen to the current? If I have put an up arrow on one side, I have to put an up on that side too. So if I increase the volts, I increase the current. Let's play another game. Let's get rid of these arrows. If I increase the resistance, if resistance goes up, as the denominator grows, the current will decrease. So we can use this equation to tell a story. Not only to just plug and get numbers out, we can use this to make predictions of phenomena. Solving the next problem, let's move on. Flashlight has a resistance of 30 ohms, so that's R, and a voltage of 90 volts. What is the current in the flashlight? Again, I is V over R, and that's 90 volts over 30 ohms. That is 3 amps. Reveal the answer, and we're good to go. Nice work. Keep going. What is the current in a wire whose resistance is 3 ohms if 1.5 volts are applied? So again, solving for I, it's V over R. So we have 1.5 volts applied across 3 ohms. 1.5 over 3 is 1/2 of an amp. Volts over ohms are amps. Now we're going to vary this. How much voltage is needed in order to produce 7/10 of an amp of current through a 490 ohm resistor? We'll start off by writing Ohm's law, I equals V over R. Let's erase that. I want to write this to clearly note which variable is in the numerator, that's voltage, and which is in the denominator, resistance. I'll rewrite I is V over R, and if we want to isolate V, we're going to multiply both sides times R, which will cause cancellation, and I'll rewrite V is I times R, so the voltage will be the current times the resistance, and that is 7/10, 0.7 amps times 490 90 ohms of resistance. Save the calculation. I'll just reveal the answer. 343 volts. How much voltage is needed in order to produce a half of amp through 150 ohms? Again, I just showed the manipulation, so I'll rewrite the formula. V equals IR, solving for V, given I equals V over R. And the current is 1/2 of an amp times the resistance, 150 ohms. 1/2 times 150 are 75 volts. What is the resistance of a rheostat coil? A rheostat is simply a dimmer switch. If 0.05 amps of current flows through it when 6 volts are applied across it, that's wordy. So we're going to solve for forward resistance. I is V over R. So we'll multiply both sides by resistance, and that will leave us with V equals IR. So we want to get R by itself. So I'll divide by I, cancel, and it will leave us with the equation R is V over I. So again, this is still Ohm's law. We're just solving for different variables. And we end up with 6 volts and 0.05 amps. Make that decimal a little more pronounced. 6 divided by 0.05 or 120 ohms of resistance. And what should be the last resistance problem, given R is still V over I? We end up with 1000 volts applied across 20 amps. 1000 divided by 20. Oh, let's just do a little cancellation. Cancel the 0, cancel the 0. 100 divided by 2 or 500 ohms. Let's practice drawing that omega. Oh my. Flat line, go up over the top and then over. So you can see that omega is not listed in this problem. 500 ohms of resistance. Ruh-roh. I made a little mistake. Let's just double check. Whoops, 100 divided by 2 indeed is 50. Oh, let's fix it. I meant to do that, so I'll put a decimal right there. I meant to do that. Sorry about that.